Hi students, today we will discuss about the concept of rational numbers and their decimal expansion. Under this topic we will cover statement of three theorems and the problems related to the statement of these theorems. Before that we will discuss the concept of rational numbers and decimal expansions. If you haven't watched my previous videos, then please watch them by clicking the I button on the top or simply click the links in the description. So, decimals. A decimal number can be defined as a number whose whole part and fractional part separated by a dot, and this dot is called decimal point. Example: 1.5, 2.24, 15.106, 1.666 and so on, 2.14587996 and so on. Now, types of decimals. The first one is terminating decimal. So terminating decimal, example 1.01245. Here this decimal terminated 5, so this type of decimals are called terminating decimals. Second one is non-terminating recurring decimals. Example 1.1212121212 and so on. Here 12 recurs infinitely, so these type of decimals are called non-terminating recurring decimals. Third one is non-terminating and non-recurring decimals. Example 9.49412728479811 and so on. Here the fractional part going infinitely and no number is recurring. Rational numbers. The numbers which of the form p by q or which can be expressed in the form of p by q, where p comma q are integers and q not equal to 0 are called rational numbers, denoted by q. Examples of rational numbers. All integers are rational because every integer can be expressed in the form of p by q, that is 2 can be expressed in the form of 2 by 1 or 0 equal to 0 by 1. And fractions. Fractions are also rational numbers because they are in the form of p by q only. Example 2 by 3, 7 by 5, negative sign of a fraction minus 11 by 2 and so on. Next one is decimals. In decimals, terminating decimals also rational number. Example 1.25 minus 0.698 and so on. And non-terminating recurring decimals also rational numbers. Example 2.575757 and so on. Now we will discuss the theorems. Theorem 1.2. Let x be a rational number whose decimal expansion terminates. Then x can be expressed in the form of p by q, where p and q are co-primes and the prime factorization of q is of the form 2 power m into 5 power m, where n comma m are non-negative integers. Let's understand this statement through an example. Take a rational number x is equal to 0.15. Now x can be expressed in the form of p by q. There are two places after the point, so we can write x is equal to 15 by 100. Writing this fraction in least terms, so by cancelling the numerator and denominator in 5 table, we have x is equal to 5 3s are 15 by 5 20s are 100, 3 by 20. Now we will prime factorize the denominator value q is equal to 20. 20 is equal to 2 into 5. So 20 can be written as 2 square into 5 to the power of 1. It is in the form of 2 power n into 5 power m. Now I will correlate the example with the statement. Let x be a rational number we took 0.15, and this can be expressed in the form of p by q, that is 3 by 20. Then the denominator is of the form 2 power n into 5 power m. Now we will discuss the second theorem, theorem 1.3. Let x is equal to p by q, where p comma q are co-primes, be a rational number such that the prime factorization of q is of the form 2 power n into 5 power m, where n comma m are non-negative integers. Then x has a decimal expansion which terminates. Let's understand the statement through an example. Take a rational number x is equal to 3 by 20. Prime factorization of 20 is equal to 2 square into 5 power 1. So which is in the form of 2 power n into 5 power m. Now let's see the decimal expansion of this rational number. For that, let's do the division. Divide 3 by 20. We'll get, put 0 point and write a 0 beside 3. 21s are 20, remainder is 10. Again, write 0 beside 10. 25s are 100. The remainder is 0. So the decimal expansion of 3 by 20 is 0.15. That is we got decimal expansion which terminates. Let's correlate the example with the statement. Take a rational number 3 by 20. The denominator is in the form of 2 square into 5 power 1, that is 2 power n into 5 power m. Hence we got the terminating decimal expansion of the rational number. Coming to the next theorem, theorem 1.4. Let x is equal to p by q, where p comma q are co-primes be a rational number such that the prime factorization of q is not of the form 2 power m into 5 power m, where n comma m are non-negative integers. Then x has a decimal expansion which is non-terminating repeating decimal. Let's understand this theorem through an example. Take x is equal to 7 by 6. The prime factorization of 6 is as follows: 2 power 1 into 3 power 1. Is it in the form of 2 power n into 5 power m? No, this is not in the form of 2 power n into 5 power m. Now let's check the decimal expansion of this rational number. Divide 7 by 6, we get 6 1s are 6, remainder 1. Put point here and write 0 beside 1. 6 1s are 6, remainder 4. And write 0 beside 4. 6 6s are 36, remainder 4. Again put 0. 6 6s are 36. If we continue the division, then we get 6 infinitely. Therefore, the decimal expansion of 7 by 6 is 1.166666 and so on, which is non-terminating recurring decimal. Now correlate the example with the statement of the theorem. We took the rational number as 7 by 6 and the prime factorization of the denominator is not in the form of 2 power n into 5 power m. Hence we get the decimal expansion of the rational number which is non-terminating recurring decimal. Now we do some problems which are based on these statements of theorems. Question: without actually performing division, state whether the following rational numbers have a terminating decimal form or a non-terminating repeating decimal form. Question number 1. 23 by 2 cube into 5 square. Students, can you guess, is this rational number has a terminating decimal form or non-terminating repeating decimal form? Yes, you are exactly right. The denominator is in the form of 2 power n into 5 power m. Hence by a known theorem which is previously discussed, hence it has terminating decimal form. Question number 2. 129 by 2 square into 5 power 7 into 7 to the power of 5. Students, can you guess, is this rational number has a terminating decimal form or non-terminating repeating decimal form? Yes, you're right. The denominator is not in the form of 2 power n into 5 power m. By known theorem, it is non-terminating repeating decimal form. Hence, it has non-terminating recurring decimal form. Question number 3. 11 by 12. The denominator 12 is equal to 2 square into 3 power 1 is not in the form of 2 power n into 5 power m. Hence, it is also non-terminating recurring decimal form. Hope you understand statements of these three theorems and the problems based on the statements of these theorems very well. If you like the video, please support the channel by subscribing so that I can make more and more videos. If you really like this video and found helpful, then subscribe to this channel and click the bell icon. Like this video, then share this video with your friends because this video may be helpful to your friends also. And don't forget to post your valuable comments here. Finally, thanks for watching.